Hello everyone, and welcome to my very first video of programming, and today I'm going to talk about template metaprogramming. I'm gonna start off with the basics. So how do you instantiate templates, and what are they for? I'm gonna just show some examples of their use cases. So I'm just gonna dive right into it. Let's just say you want to have a generic kind of class, and it has to contain an array of integers. Let's say it has to contain a certain amount of integers, right? So let's just start off with a naive implementation of maybe how you would do it in a quote-unquote regular scenario. So let's just create a class. I'm expecting you to be familiar with classes. So let's just start off with a class called int array 100, because it's gonna contain an array of 100 integers. You see AI already created that for me. Well, okay, let's just set these values right here, and let's just actually return a reference so we can change the value of the underlying array. Well, obviously we're gonna instantiate it right here. So it's gonna place 100 integers on the stack. Then index 5 is gonna be set to 10. And then we query the element on index 5, which is gonna print 10, obviously. And then return 0. So let's just execute this program. It's gonna print 10, obviously. Alright, so it prints 10 here. So what if I wanted to create a class that contains 100 floats? Well, okay, we're just gonna create another class. It's called float array 100, and well, it's gonna be exactly the same as integer array, except it contains floats instead of integers. Obviously there isn't, according to the naive and quote-unquote naive implementation, there isn't a generic way to make this some sort of variable. Well, not yet anyway. I'm going to show you just in a moment, but you know, the point what I'm trying to make is this is not variable, right? So let's just create the float array right here, print out the value. It's gonna print 2 times 10, except the other one is a floating point, which it doesn't show on the console, obviously, because it's 0.0. So the other one is an integer. But what if I have a custom type called I don't know, strict custom type, and it contains some values, and then I'm gonna create another class called custom type array 100, right? So you see the point where I'm getting to is we're doing the same thing over and over again, and we actually don't want to do that because we don't have to, and it's very verbose to create infinite amounts of classes for your very specific use case. So let's just remove all this and create a template. So templates are created like this. Then either type name or class can be typed, and you give it a name, say T. So let me just remove this operand, or let me just remove this character. Let me also just remove type name. So you can either write type name or class. It doesn't matter in this context. It doesn't matter which one you're going to type. So it may be class, maybe type name. I always write class because it's less typing. But you can go ahead, write type name, whatever you want. But I'm gonna stick with class. So class means that it can be any type, right? So it may be, so T is the type. It's your variable. It's either your int or your float, and the class identifies that we are talking about types, right? So any type, and we're giving it a name T. So everywhere where T is referenced is replaced by the actual type. So float, int, custom type, short, unsigned, whatever. This is any type, right? So let's just create a class called any array 100. So this is gonna be an array of 100 elements with the type T. So T is either float or int, whatever, depending on how you instantiate it, which we're gonna do later. So what I just said earlier, everywhere where you reference to T is a reference to the actual variable, quote unquote variable type. So we did int array something right earlier, right? But now the int part is variable, so we can replace int with T. So T means any type in this context, because we wrote class here, or type name, doesn't really matter, but I'm just gonna make it class. So T refers to any type, right? And now we're gonna create the same methods as we have created earlier, which were, I think, void set value, which is gonna have an index. Let me just change this to size type, just more C++ way of doing things, or a more correct way anyway. And a value, and T is referring again to this T. So these, everywhere where T is referenced, it is the same type. So if T is an int, then this T is replaced by an int, and this T is replaced by an int, and anywhere within this class T is referenced, the type is actually replaced, the actual type is actually replaced by it. Right, so again, we're gonna have a get value, which is gonna return any type again. Well, okay, we're just gonna query the array and return the element on a certain index, which returns anything, this can be anything, right? So right, let's create an any array 100. Let's just not type all this, it's way too much. So we're instantiating an any int array 100, so it's gonna place 100 integers on the stack, and we call it int array. So this int is passed, right? As T, it's passed, you know. So everywhere where T is, it's gonna be replaced by int, right? So let's just say int array set value 10, 0, index 0 of value 10, and we're gonna print it, and then we're just exiting our program, and obviously it's gonna print 10, obviously, right? Because we just set value to 10. But we still have hard-coded, sort of hard-coded, the amount of elements in our array. So what if I didn't want to have 100 elements in my array, but 128? All right, let's just create another class. Yeah, we're just gonna do it naive first, and we call it any array 128, and this has 128 elements. Right. So this is very naive and also very bad practice, because we can solve this way easier and less verbose. We can do that by adding another argument to our template. And as I just said earlier, class means any type. So it can be integers, it can be floats, it can be custom types, it can be anything. But you can also pass primitive types. So a primitive type is, say, a size, and well, we want to pass how much elements are going to be in our array. So that's what we're doing here. We're saying, all right, the first argument of our template has to be a type named t, and as second argument we have to pass an argument, an actual value of type size t. We're just gonna call it n, and you see this red squiggle right here. It says too few arguments for class. That's because we just added another argument called n with this has to be a number, and like this has to be a type, and this has to be a number, because we're saying this is an actual type. So we're just gonna pass a number right here. Let's say 1024. So we're saying let me just remove this because it's not 100 anymore. So we're creating an array of type int with size 1024, but we haven't done anything yet with this n. So this, everywhere where n is referenced, this value in this specific case is referenced. So let's just put n right here. So we don't know how much n is in this context. We also don't know what the type t is, but we're not interested in any of that, because we just want an array of a certain type with an n amount of that amount of t's. So right now we created an array of a type with n elements, and let me just put these curly braces right here so everything gets default initialized. So now we have created this array of integers with size 1024, right? And we can set a value, and the output of the program will be the same, obviously. Let me just add another parameter called size. That's exactly what I wanted to do. So the same counts for n as for t. So what I said earlier was everywhere where n is referenced, the actual number is being replaced by it. So I wrote 1024 here. Everywhere where n is referenced, it will be replaced by that actual number. So this is what it actually will be replaced by, but let me just put that right back. So this is just sugar, right? This is syntactic sugar for us. The compiler is doing the actual work, because the compiler knows. All right, so you want to create a template of integer with 125 or 1024 elements. All right, I'm gonna make that for you. So he is gonna use this as some sort of blueprint or template, hence the name, and create a very specific instance of this class with these types. And the way the compiler does that is as follows. This is the compiler. You don't actually see the compiler do it, but it does do it. But it just does it behind the scenes, you know. All right. So what the compiler does is it creates an empty template. It's then creating a class for you called AnyArray int 1024. This is what the compiler is going to write. All right, you're seeing these red squiggles right here. That's because we specialized an AnyArray of type int with 1024. So first, the compiler is going to check, are there any implementations of AnyArray with type int and n equals 1024? Well, yes, it does actually, because it's right here. It has it's a specialization. It's a specialization of the generic class AnyArray. We haven't. This is not inheritance, you know. So these functions are not included in the specialization of this class, because this is just a new class in some sort of. It's just actually a new class. You're writing an entire new class. The only difference is that the compiler knows to use this implementation, this specialization. So if you want to specialize only for integers with size 1024, then use this implementation, right? But it doesn't have these functions yet, as you can see. It has no member set value. That's right, because it doesn't. We just created some sort of new class. So if you want to actually create these functions, you have to write them yourself, because they don't exist yet. And now it says, oh, okay, AnyArray with type int and size 1024 is specialized, and it is right here. So it's just like function overloading, sort of. The compiler is going to check which functions match the best in your use case or in that use case, and that also counts for template specialization. The compiler is going to check, are there any blueprints, so to speak, for this very specific use case? Well, yes, there are, because it's right here. All right, then I'm going to use this. The compiler is compiling that for you, right? So let me just execute the program. It's going to print 10, obviously, again. Right, so, but what if every time we call the function setValue for this specialization, what if I wanted to print something, but for the generic implementation I don't? So let's just say let's just make it a little bit easier. Let's just say any type, right? And it's gonna be a type, and then it says void print, and it's gonna be const, and it's gonna print the type, and that's basically it, right? Okay, so let's just create any type int a. All right, a.print, whatever, it's cool. It's gonna print 0, I think. Yeah, 0, correct. So what we did here is we created a different class with a type t called type, obviously, and in print we're printing the value, and we write a new line, we flush it as well. So this isn't very different in the example I showed you earlier, but what I'm going to show you is the pretty cool things you can do with template meta programming and specialization and stuff. So we created an int, any type int, right? But what if I want to print the type. What if I wanted to print the type? All right, so let's just say I don't know what type I am, because we don't. I mean, we know we're passing an int right here, but what if we create another one? There's no way of knowing what the type is here. At least I'm going to show you how you can query the type, sort of. But for now, we don't know what the type T is. We know it's a certain type, but it's very abstract. We don't know anything about it. So there's just this way you can sort of find out, and that's with the specialization again I showed you earlier, with the int and 1024. We're gonna create an empty template again, and then let's just say class anytype int, obviously, and then let's print C. We know that the compiler will choose this implementation over this implementation when passing an integer, obviously. So now we know, okay, the compiler chooses this implementation when an integer is passed, so we know for sure that this is an integer. So we can print I am an integer, obviously, because it's an int. Let's just say let's just add let's just make this a struct, so we can give the string a value. Hello, yeah, that's good. And give the integer a value of 10,000. And let's create another specialization for string. So we just did the exact same thing for string as we did for integers, right? So let's just create another anytype, and it's gonna be a float, and well, it's gonna be pi, all right. And then we're gonna do a.print, b.print, and c.print. So let's just see what the program prints. All right, so first of all, let me just clear this, then we get a clear output. All right, so yeah, obviously it's gonna print two things, obviously, so I was a little bit confused here, but all right, a.print. A is an anytype int, so it prints integer. I am an integer, it prints, and it prints the value 10,000. That's correct, because that's the value we have given it. Then b.print will print I am a string, because we have our specialization right here for string, and it's gonna print hello because that's the value. And then we are going to create an anytype float called c with the value pi, and it says I don't know what type I am. Well, why would you think that is? Well, it's because we haven't created a specialization for anytype float, which we have done for string and int, but we haven't done it for float. So the compiler is going to create this blueprint, just as for integers, but the implementation of the function doesn't change. So what the compiler does is it's gonna take the print implementation, so it just copy paste this like this, and it's gonna be an empty template, and it's gonna create it for floats, obviously, and then here t is replaced by float, and that's all the compiler does. So it changes t to float, it doesn't change the implementation. So obviously when I run the program once again, it's gonna print I don't know what type I am, because we haven't changed the implementation of the function, so the output is going to be exactly the same. Unless we change the print statement right here, so I'm a float, and it's gonna print I'm a float, obviously, here, and print 3.4. But if we remove this, then it's gonna print I don't know what type I am, because we haven't created an implementation or a special implementation for any type with float, like we did with integers and strings. So you can do lots and lots of stuff with this, but this is just the very basics of the template metaprogramming thing, and I'm planning on making more videos. So let me know what you think, and I'll see you next time.